In this part, we see the basics of facial animation and in particular the notion of blend shape. Facial animation of virtual human is both very common on animation production and particularly hard to model. First, because real human faces have a large number of muscles, about 100, so that we can generate lots of different facial expression. And second, as humans, our perception is extremely sensible to the face of other humans, much more than for other parts of the body or for non-human face. Which means that animating plausibly a human face requires usually much time and more care than animating other type of elements. And there is further another perceptual problem, which is the so-called uncanny valley effect for faces. So the principle is the following. If we start from a representation that is very far away from human trait, like an industrial robot, our perception is rather neutral. It looks like a robot and we don't feel attracted nor repulsed by it. When the representation improves toward more human traits, then our perception tends to be more attracted toward it. Typically with stylized figures like 2D cartoons that we can find cute, while still being far from being realistic. Then if we continue to improve and refine the representation with more realistic characteristics and detail, at some point something strange happens. As humans, we are going to feel less comfortable by the represented virtual character, or even repulsed by it. Somehow we see something that looks realistic in most parts, but lacks some real-life details. Sometimes we don't really explicitly know what is actually lacking, but we just feel that something is wrong, like if the model was looking like a dead person or an animated zombie. And this is what we call the uncanny valley, and we should avoid to reach this state. But it happened a lot in the first photorealistic animated movie attempts. A few famous ones for odd-looking characters are, for instance, the Final Fantasy in early 2000, Polar Express in 2004, Beowulf in 2007, and other movies with cheap visual effects. And this also happened in the robotic industry, when dealing with human-looking robots that end up looking more creepy than friendly at some point. But then if we continue to refine again and again the character in order to add all subtle details on human face, then at some point we pass this uncanny valley and reach a point where the face really looks photorealistic and alive. But reaching this point is quite hard and requires lots of efforts. We can also note that this uncanny valley exists both for static shape and animation, but its effect is even more sensible for animation, as a lack of detail in the motion of a perfectly photorealistic 3D model would look very odd. So to ease the generation of facial animation, artists have noted that human expression can be categorized, like fear, happiness, surprise, and so on. And one of the ideas is to spend time modeling carefully the main expression of the model as they are in limited numbers, and then we generate an arbitrary animation in interpolating between these main expressions. So the process of interpolation in itself is easy. We simply apply it to every vertex of the mesh, as the connectivity is supposed to be the same among different expressions. For instance, we can take two basic poses, B1 and B2, and in this example we interpolate linearly between these two positions. And we can call the interpolation weights omega1 and omega2. In this case, omega2 is equal to 1 minus omega1, as there is only two poses. But we can go further to mix different facial poses together. We can actually consider multiple poses and do a blending between them all together. This is called blend shapes or multi-target blending. This allows, for instance, to do a mix of happy expressions with surprised one and tired one. So we are basically evolving within the n-dimensional space of bases described as the key face expressions. So the formulation remains straightforward, as it's a simple barycentric interpolation, saying that the position P of vertex I at time t is given by the sum over all the poses k of the weights omega k at time t multiplied by the vertex position bik for the basis pose k. And of course, in this case, the sum over k of all the weights omega k should be equals to 1. Another way to express this barycentric relation is to use a matrix form and say that P is equals to B omega, with this time P being the big vector containing all the vertices of the mesh, omega is all the n poses weights, and B is the tall matrix with all the position of all vertices in column and all poses in row. Another often more intuitive way to work with blend faces is to express it as coordinate differences instead of barycentric blending. Indeed, it's often simpler to start from a neutral pose and then add or remove some expression like adding some smile, opening more or less the mouth, opening the left eyes, and so on. So to this end, we consider B0 to be the neutral pose, and then we pre-compute the pose differences dk as bk minus b0, which are the position of the pose k minus the position of the rest pose. And then we can compute the deformation along time as pi of t is equals to b0 at vertex I plus the sum of all the poses of our weights omega k of t times the difference d of vertex I of pose k. And this is the result you can see with the slider, where the user can dynamically increase or decrease the amount of expression with respect to the neutral pose. And this part will be subject to a lab class exercise. Also, we can finally note that this relation can also be expressed in matrix form, with this time a tall matrix of position differences D. As a summary with blend shape, this is the standard approach for modeling facial deformation, and it can also be used to model general shape deformation. It allows to add or subtract local expression given by preset poses, or even extrapolate these. It even allows expression transfer. Once we have encoded the vertex differences dik, we can apply it to another face that shares the same connectivity. This is used often in video games, where there is several characters with different face geometry and texture, but similar mesh structure. Several animation software include by default blend shape tools, and it's common to deal with this type of sliders to navigate through the space of blend shape. It can also be used to model automatic speech animation, where each element of sound relates to a specific placement of the lips, and this is called VSEM. And then associating VSEM to a text and interpolating the lips along this key position allows to generate the motion of the speaking face. It's however not a perfect method, so to work well the poses should avoid redundancies to not interfere together. However, it's not the case in general. For instance, the matrix D is not an orthogonal matrix. So different weights can actually give the same result, and some combination can interfere together. So one way is to use a PCA type of approach to orthogonalize the basis function, or the matrix D in this case. But then the weights are less intuitive to use. In particular, they would not be restricted to positive values in this case. And if you want to know more about blend shape, you can have a look at this Eurographic state of the art from 2014 on the use for facial animation.